evening, everybody. Continuing from the last lecture, today we are about to discuss another interesting concept. So far, we have seen mirrors of all sort. We have seen plane mirror, we have seen concave and convex mirror. And one thing that is very common about all kinds of mirror is that light reflects of them. So reflection is essentially the concept that was there, or that was a phenomenon light was doing so far. Now we are about to make an exception. We're about to enter a new realm, something new that the light does. What is that new thing that the light does? Well, first of all, I would like you to see certain examples. And first of all, think about it, whether there is some reason behind it. And then I'll present you the phenomena that I'm talking about. So, what I'm about to present to you today is following. All of you must have observed this multiple times that there's a straw in the glass, and when you put it, this is how you see. Ever wondered what is the reason why the straw appears to be different inside the water than from what is outside the water? And we all are aware about the splitting of light into 7 colors. Well, there is something common between these two, although they look pretty different from each other. And something that is common is light is coming from water and entering our eyes, which are in air. So there is a transition between the mediums. Light comes from water to air. In case of glass prism, again, the same kind of transition actually exists. Light enters from air into the glass, a medium change, and later on it again changes from glass to air, comes back. Similar thing can be seen with the glass slab. In that also, light enters into the glass and then come out again into the air. Wherever light is undergoing transition from one medium to another, something interesting happens. As visible, especially in the example of this glass slab, you can see first of all the light ray bends. As you can see, the light was sent horizontally. But can you all see that? It didn't follow its trajectory. So what it did, rather? Well, it bent. It should have continued straight, but no, it bent. And after coming out, it should have also continued straight like this, but again it bends. So first this way bending, in the second case this way bending. So one thing is clear, that the light ray bends when goes from one medium to another. And this bending of light causes really interesting things to happen, the examples of which we have already seen. So takeaway from here is, when light enters from one medium to another, it bends. And this phenomena of light going from one medium to another is called as the refraction. So for the first time, we enter into a new phenomena with light, and that is refraction. Now, there are two major kinds of bending that are seen, which you saw in the glass slab also. And how do we define these two types of bending? Well, you can see in the first case, light is entering from air to glass. And we define a normal line. Here you can see, this is our normal. Why it is called as the normal? Because the interface on which the light ray has fallen, to that interface, this normal is perpendicular. That's why it's called as normal, just like in law of reflection also we had. So the angle that the incident ray makes with the normal is called as I. And then light ray will going to go into the other medium. It will enter the other medium. And then now the angle that it will make with the normal will be called as the angle of refraction. So normal is a common line, just like we had in reflection. If here it is similar to light getting reflected. Imagine if light would have just gone from air into the air. We would have called it reflected ray. And then we would have said, if this is I, then this is also I, isn't it? That was law of reflection. But for the first time, it's entering into the other medium. So we're calling it refraction. And now we name it as refracted ray. So there are two types of bending. When comes from air into the glass, we say that the light ray clearly bent towards the normal, as you can see, because ideally it should have gone straight like this, but what we saw is bending towards the normal. And in the other case, the exact opposite, from glass when it goes into the air, it bends away from the normal, because you see, ideally it was supposed to travel straight, but it bent away from the normal. So in this case, angle of refraction is greater than incidence. In the first case, angle of incidence is greater than angle of refraction. So these two kinds of bending are clearly observed. The example was clearly this glass slab. So here, if I ask you where is the normal, so now this is the interface, glass air interface. So our normal should be like this. So I would say this was the incidence angle. And what is the refraction angle? So what the final refracted ray makes with the normal, that has to be the refraction angle. This is R and this is I, what they have written. And what about on the other side? So this is the normal to the interface, this one. This would be the incidence angle. This would be the refraction angle. This is how the refraction works. Where can we see the direct applications of these two types of bending? Well, this is the reason whenever you must have observed the base of a swimming pool, it must have appeared you shifted a little up. The depth appears to be a little lesser than what it actually is. This phenomena happens because of the bending of light. This schematic diagram actually shows you. So whenever you see an object which is underwater, you are outside in air. The object is underwater. When light will come from the object to you, it will undergo a medium change from water to air. And because of this bending of light, the image actually appears to be up. Object actually appears to be up because you are no longer observing the object anymore. You're observing the image. That is the reason why that straw inside the glass appeared to be bent, because you're no longer observing the actual straw inside the water. Inside the water, what you're observing? You're observing its image. Outside, you see the object. Inside, you see the image. That's why you see inside water, the straw is bent for this reason. And the opposite can also happen. You are underwater and you observe the outside world. And I don't know if you ever tried it, but fortunately, I've been able to get a picture which gives you exact view what you get from underwater when you're inside the pool. And this is how it actually looks like. And you must have also experienced this. Just see how it is appearing. Things appear to be kind of stretched from their actual height, isn't it? Kind of pretty wobbly when you see from inside. All this is happening, remember, behind all of this is light bends when it goes from one medium to another. Now, question arises, why does it bend? Why can't it move straight while changing the medium? Well, the reason are pretty deep. It involves the understanding of electromagnetic radiation and their wavefronts. But on our level, we can understand it by this logic that one thing is for sure, and that is light travels with different speed in different mediums. Like take for example, at what speed you can run in air will be very high. Let's say you're very athletic. But if the same person, same you, is being told to now run inside the water, will you be able to run with the same speed? You won't be able to. Reason? Because the medium changed. Different medium offers different kind of resistance to us. So that same thing happens with the light. Light travels fastest in the vacuum. It travels with the speed of light, as we know, 3 into 10 raised to 8 approximately meters per second. Apart from vacuum, when it will enter any other medium, it will just slow down. So in glass, it will slow down. In air also, only a little change is there. Between air and vacuum, not much of a change, only slight. But in glass, water, and other kinds of medium, change is pretty major. It falls down by a huge amount. So now we define a quantity which is called as refractive index. Refractive index actually tells you about how much the light slows down in a certain medium. So as you can see here, the definition also, by logic in vacuum, it's 1, because in vacuum it travels with value C only. So C by C will give you 1. But in other medium, let's say here, how the refractive index would be defined? It would be defined as the speed of light in that medium, and in numerator you will have speed of light in vacuum. All right. So that's refractive index. So I hope this must be clear. Now think about it. Since V is always lesser than C, because in vacuum light travels faster, C is the maximum speed light can move. All other values V will always be lesser. What do you realize from here? This refractive index always has to be greater than 1 for all the mediums. Refractive index can never be less than 1. It can only be equal to 1 only for vacuum. For all other, it's greater than 1. So some of the common I can write here, like air is very near to 1. In reality, somewhere 1.003, but we can take it almost as 1. When you talk about water, the refractive index is 4 by 3, that is 1.33. If you talk about glass, well, actually, it depends upon the type of glass also, but the general glass that we see, it's 1.5. So depending upon the medium, the refractive index also starts to change. Now, is there a law that can actually relate the two kinds of bendings, or that can relate the incidence angle with the refraction angle? And this is very important because in reflection, we had the law of reflection, which could tell us I equals R. Now, theta 1 and theta 2 are different. How do we know the relation? So relation exists, and it is named after great physicist Snellius, and the name is Snell's law. And what this law talks about, it says you need to know the refractive indices of the two mediums from where to where it's going. And then you have to check their angles. What is the angle in one medium? What is the angle in the other? And Snell's law is simply the product of, like I always tell people to remember it like this, refractive index of this medium, N1, times sine of angle of this medium, N1 sine theta 1, is equal to refractive index of other side equals sine of angles on the other side. That becomes Snell's law. Now, Snell's law is not only limited to this, because from here we can see the ratio of refractive indices is sine theta 2 by sine theta 1. But we also got to know that refractive index is ratio of speed of light over the speed of the light in that medium, right? So I can write that in the previous case, you clearly saw refractive index is inversely proportional to the speed of light in that medium. C is always constant. So since there is an inverse relation between refractive index and speed of light, I can write it as V2 by V1. You can see inverse relation with N1 and 2. All right, just from this expression. And light is a wave, and every wave follows a law. What is that law? V equals F lambda. F is the frequency, lambda is the wavelength. Now, when light enters from one medium to another, it's important point to note that wavelength may change, speed may change, but frequency remains unchanged. Frequency cannot change while making transition. The reason behind this lies in the photon theory. So right now beyond the scope. So V equals F lambda. When I substitute here, F lambda 2, F lambda 1, you can clearly see F gets cancelled. So we also get an inverse relation with wavelength. Refractive index is inversely related to wavelength. So this is the complete Snell's law. And there could be easy questions done on Snell's law itself. Take, for instance, this. Light is entering from air into water. So this is how the light ray comes. So you can see I've already drawn the normal. Always draw the normal. And let's say I give you it is coming at an angle 30 degrees. Find the refraction angle. Now, first of all, light will bend towards the normal in this case, as we already have seen. So this refraction angle is what I need. I can use Snell's law, but I need refractive indices. Well, for air, as I said, it's almost 1. What about for water? For that, it's 1.33, which is actually 4 by 3. So Snell's law, refractive index of one side, sine of angle of that side, and so on. So 1 into sine 30 is equal to, on the other side, 4 over 3 times sine of r. And sine 30 is 1 by 2. So what do I get the sine r value as? It comes out to be 3 over 8. So I got the refraction angle as sine inverse 3 by 8. If we don't have a calculator, then we can leave it till here. If we have a calculator, we can find the value of this angle. All right. So easy to use Snell's law. It's not necessarily all the time you have air and water only. Many a times you might also have two different kinds of medium. Like you can see here I can put glass and here I can put water. And let's say I tell you the light comes from glass and goes into the water. Now glass is having refractive index of 1.5, which is 3 by 2, and this is having 4 by 3. Now how do we decide which side the light ray would bend? So there is a simple logic. The mediums with higher refractive index are called as denser medium. Whenever refractive index is higher, we call it the denser. And whenever it is lower, we call it rarer medium. Just like we use for the density. So among glass and water, which one is having more refractive index? Obviously, glass 1.5 is greater than 1.33. So here glass is denser and water is rarer. But again, it's all relative. All right. So if you look at the same condition in air and water, here air was rarer and water was denser. So there is a simple logic that you can remember in order to find out where the light ray would bend. Whenever light ray goes from rarer to denser, it always bends towards the normal, which I have drawn in this case. And whenever light ray enters from denser to rarer, the opposite, it will always go away from the normal. So refraction angle will be greater. All right. Although we apply the same logic, let's say here also it comes down at 30 degrees. So I'll use the same law. 3 by 2 sine 30 equals 4 by 3 sine r. Again, sine 30 is half, and I can see 9 over 16 as the value of sine r. So easy to use Snell's law. Moving ahead, as we now know, when light enters from denser to rarer medium, it bends away from the normal. So here, let's say I have placed an LED under water. Water is denser and outside is air, which is rarer medium. So when light ray actually falls perpendicularly with normal, it makes 0 angle. So refraction angle is also 0. That happens in both, remember, in reflection also and refraction here also. If incidence is 0, refraction is also 0. If incidence is 0, reflection is also 0. So whenever light ray falls perpendicularly to a medium, it just passes without any deviation, like this, which is you see in the first ray. In the second case, now it falls at an angle. So you can see it went away from the normal. Theta 2 is clearly greater than theta 1. But imagine I keep on increasing the angle with the normal. Suppose I further increase the angle. This is even greater than theta 1. It will further go away from the normal. It'll keep on going away from the normal. And how much it can go away from the normal? When it can become even parallel to the interface. We say, in this case, light starts to graze the surface. Now, as a matter of fact, it's just moving in between the two mediums. We can't even say in which medium it has gone. Now, the moment the angle at which this happens, this theta c, you can see when incidented at theta c, it's grazing the surface. Or other way to put it is, refraction angle becomes 90 degree, right? So the angle at which this happens is called as critical angle. So there is a certain angle, critical angle, when you reach that value, light suddenly starts to graze. That is, refraction angle becomes 90 degrees. So how do we find this critical angle? We can use Snell's law. R is 90 and incidence angle is theta c. Just apply Snell's law. N1 sine theta c is equal to N2 sine 90. Now, in most of the cases, the rarer medium is the air. And if rarer medium is air, then what is its refractive index? 1. So N2 becomes 1. And so sine theta c simply becomes, sine 90 is also 1. 1 by N1. And now let's just call it N, because there is no N1, N2 anymore. So critical angle is always 1 over N. Always in the sense when the rarer medium is air. If it is something else, it will be different. So you should always remember the logic. Logic is using Snell's law. Now, interesting thing would happen if you exceeded beyond theta c. Now you further increase from theta c. So more and more it will want to go away. And in that case, it starts to reflect. So suddenly light ray starts to come back in the same medium where it is started from. And so that is what we call as total internal reflection. Now it's reflecting. So whatever theta you incidented, same it's reflecting. Light doesn't even enter the air. All right. That's the best part about it. Here is an image that actually shows you practically. Can you see how amazing this picture is? Laser is incidented from under the water, but not coming outside in air. Just goes back into the water only. That's the best part about it. And if you arrange it in a proper way, you can actually repeat this kind of reflection as what you see in this class lab. They have sent in this site and it is constantly getting repeated. And guess what? When you see this, light is an electromagnetic wave. If electromagnetic wave can remain inside this medium only, like a glass slab, like a pipe of glass, then this can be used for message propagation. What kind of message? Internet. Because internet message signal is also electromagnetic wave. So if I create a cable in such a way that it always keeps on getting reflected inside only the internet signal, then I created a proper way of channel to make the signal reach the other end. And that's what we call as optical fiber. This is what you must have heard about. So inside the optical fiber, message travels with the help of constant total internal reflections. So that's a very amazing addition to your knowledge. Optical fibers actually work on this principle. You can see an animation that shows you the same. How the light which came from water remains inside the water only. And it gives you the same definition in proper language. So time to do certain questions of TIR. Let's try to calculate the critical angle for water-air interface. Suppose this is water and this is air. Important point, since light ray will bend away from normal only if it goes from denser to rarer. Critical angle is only defined when incident ray is in the denser medium and refracted is in the rarer. Now I want critical angle means the other angle has to be 90 degrees. The ray will go grazing the interface. So simple, water is 4 by 3, air is 1. So apply Snell's law. 4 by 3 sine theta c equals 1 into sine 90. And that gives you sine theta c to be 3 by 4. So that's the critical angle between air-water interface. What if we calculate the critical angle for glass-water interface? Here, let's say it's glass, and here it's water. Glass 3 by 2, water 4 by 3. Light ray enters. And I want it to go grazing the surface like this, 90 degrees again. Then it will be the critical angle. Again, you have to simply apply the Snell's law. So 3 by 2 sine theta c. Hope you understand what I'm doing. Refractive index of this side times sine of angle of this side. Refractive index of the other side times sine of angle on that side. And this gives me that critical angle for glass water interface is 8/9. So that's easy concept of TIR. Let's try one more. Suppose we talk about this optical fiber cable only, how they design it. So imagine this is an optical fiber cable. You are sending the light from here, outside is air, and you want to send it at such an angle, some incidence angle, that finally after getting refracted, it then stays inside, keeps on getting reflected inside. It doesn't come out. So what is the minimum value of I should send it at so that this happens? So if you're talking about the minimum scenario will be when this side, it will be a refraction from air to optical fiber, that is rarer to denser. Here TIR won't happen. TIR can happen when again it hits from denser into outside rarer. So what is the refractive index of optical fiber? For air it's 1, but I am giving you for optical fiber it to be 1.25 as the refractive index. So what should be the condition? Well, if you want the minimum scenario, then it's fine for me if it even grazes along the surface after entering inside. So if this is critical angle, that will also work for me. And if it is greater than critical angle, then it's much better. It will just keep on reflecting. And remember, if it falls at critical here, then here also it will fall at critical angle. So constant reflection will keep on happening. So how do we relate, or how do we find the I value? We can find sine theta z, but how I? So let's see, first of all, find sine theta z. Well, that is simply 1/n in case of air and other medium. And 1/n means in this case 1.25. So what does sine theta comes out to be? What is 1.25? Isn't that 1/4? No, not 1/4. 10/4? No. What should it be? So 1/1.25. I leave that for you to figure out. So that's sine theta c, 1/1.25. What am I supposed to do after this? Well, I need to relate theta c and I. How do I relate that? So first of all, this is a normal kind of refraction. It's no longer TIR because that is from rarer to denser. So let's apply Snell's law there as well. It's coming from air, 1 into sine I equals 1.25 into sine R. But still the problem is not solved, because I got a new variable R and I want the value I. So somehow if R and theta c are related, we can get the value of I. So then I see in this triangle over here, 90 degrees, that it's a right angle triangle. And so I clearly get by angle sum property, R plus theta c plus 90 must sum up to 180. And then we realize R is 90 minus theta c. And so that's great. Now we can substitute it here. Sine of R, which is 90 minus theta c. And what is sine of 90 minus theta? Well, yes, it's cos theta. Now you're required to find out the value of cos theta. How would you approach that? you have sine theta c with you, isn't it? So how would you get the cos theta? Just make the triangle. So sine theta is 1 by 1.25. 1.25 is 5 by 4. So the reciprocal of that will be 4 by 5. So sine theta c is 4 by 5. If I make a triangle here, if this angle is theta c, sine theta should be this. Then obviously the base has to be 3. So what is the value of cos theta c here then in this triangle? It's clearly 3 by 5. So let's substitute 1.25, which is 5 by 4, times cos theta c, which is 3 by 5. And that gives us the final answer, sine I as 3 by 4. So that is the incidence angle at which you need to send it for constant TIRs inside. So that's it when it comes to refraction. See you all next time.